on building codes and ethics there, but let's get going with our math. So yesterday we had a little bit of a review, and we talked about our operations with measurement, setting us up for what we need to do today. And we're going to get started. We start off this class with ratios. A ratio is just a comparison between two or more numbers. We might look at my current schedule. Well, not for this week, but starting next week. We look at the days on campus, days off campus. I will be on campus 2 days a week, off campus 3 days a week. I could write that ratio in a fraction form like this, 2 over 3. I could write it with a colon like that, 2 to 3. Or I could write it with the word, that. Now when I write it with this word here, the 2 there, I have to be careful about the situation. There's 2 different types of ratios. And that word changes depending on, that wording changes depending on what type of ratio we have. The type of ratio we have here is we have 2 distinct groups. My days off campus and my days on campus are different days. They're not included in the same group. I could have, however, rather than saying my days on campus compared to days off campus, I could say my days on campus out of the week. Well, I work 5 days a week, but only 2 of those days will I be on campus. So I'll be on campus 2 out of 5 days a week. 5, or if I'm writing out with the words, it would have to be written as 2 out of 5. So when we see this wording here as out of 5, 2 out of 5, that tells us that there are other ratios implied here. One is, of course, 2 of these items, 2 parts of this setup meet the criteria that we're focusing on, out of 5 total. So this is what we're focusing on, the 2, 5 is the total. That implies that the rest are not part of the focus. 5 minus 2 means there's 3 that are not part of it. Which brings us back to this ratio. 2 that I'm on campus, 2 that I'm not on campus. So in this type of a ratio, there are all sorts of other ratios implied that we can interpret. Now that doesn't necessarily go the other direction. If you have a 2 to 3 and say, well, they're separate, we have to be careful. There might be a third category that's not included. In this case, it would be weekends. Now down here, we just said 5 work days in a week. We didn't say include all 7 days in a week. But there could be other categories that are not included in those. So those don't add up to the total. We can't just say 2 plus 3 is 5, there's 5 total parts, unless we know there are no other categories involved in the total there.
Actually going to be on it.
Actually, on Fridays, I am at Clayton High School for the day for their construction academy. But yeah, normally I'm here 5 days a week. Let's take a look at the tables in the classroom here. You've all seen the gray tables in the classrooms. They are, let's do a width to length ratio. So these are 18 inches wide and 72 inches long. Now, first of all, one of the reasons I like to express things in a fraction form rather than using the colon or the words is there are things I can do to these ratios that I am used to doing in fractions. First thing I can do is I can divide out the units, the inches, they cancel out, they're gone. All ratios are unitless, by the way. The other thing I can do is I can reduce these. Both 18 and 72 can be divided by the same number. In fact, they can both be divided by 18. 18 divided by 18 gives us 1. 72 divided by 18 gives us 4. That's 1 to 4. Now, if I had written this with a colon in it, it's 18 inches to 72 inches, I can still reduce it in that form. It's just not something we're used to seeing. We're used to seeing this reduction with a fraction. Well, we can do the same thing here. We can cancel out the inches, and both of those are divided by 18, giving us 1, 4. It still works out. It's just not, like I said, it's fractions is something we've seen before, so we just will stick to something we know how to do. We might have a ratio of, let's take a look at classes I have that are virtual compared to face-to-face. Right now, I have 24 hours of class. Well, not counting my high school academy. I have 24 hours of class in a week. 8 of those hours are face-to-face. Hours, not class. And 16 are virtual. Now I said virtual to face-to-face, so I should put the virtual first. 16 hours of virtual, 8 hours of face-to-face. Once again, I can cancel out the units because they're the same. 16 and 8 can both divide by 8, giving me 2 to 1. Now here's one of the big differences between a ratio and a fraction. If this were just a fraction, I would reduce that number just to a 2, because it's just a whole number. But it's not just a fraction, it is a ratio. And remember, a ratio is a comparison between 2 or more numbers. So I have to leave this as 2 over 1 so that I have 2 numbers being compared. Otherwise, it's not a ratio anymore. Other thing you'll notice about this is the bottom number is a 1, or referred to as 1 unit. This is what we call a unit ratio. And a unit ratio is just being compared to a 1. The second number is a 1. So this is saying it's 2 hours, 2 units of virtual class for every 1 unit of face-to-face class. You'll also notice in all of the ratios we have done so far, the units, the labels have been the same. This compared hours to hours. This compared inches to inches. This compared days to days. The units were the same in both numbers. That is a requirement of a ratio, as it must compare 2 numbers with the same units. If I have 2 feet compared to 18 inches, that's not a ratio. There's different units there. Fortunately, I can change that. 2 feet can be turned into 24 inches, 18 inches. Now it's a ratio. Inches cancel out, and I can reduce that. Both 24 and 18 can be divided by 6, giving me a 4:3 ratio. Now, once again, if this were just a regular fraction, I would want to take that 4:3 and split it into a mixed number. Do it as 1 1/3. We can't do that here. This is not a fraction. It is a ratio. Comparison of those 2 numbers. If I break it into 1 1/3, it's not a comparison anymore. This is 4:3. Excuse me. Now, the other thing you'll notice is all of our ratios, when we're done, are unitless. This is because the units don't matter anymore. What this is saying is it's 4 units in whatever that direction is describing to 3 units in this direction. I could have, when I went back here, rather than converting the 2 feet into 24 inches, I could have left that as 2 feet and did the 18 inches as 1.5 feet. Guess what? The feet will still cancel out. If I convert that, if I divide each of those by 0.5, I still get a 4:3 ratio. The ratio is not dependent on the units. If I go back to my table, I had a 1:4 ratio of width to length. The units don't matter. It doesn't matter whether I'm saying for every 1 unit, 1 inch of width, there's 4 inches of length, or for every 1 foot of width, there's 4 feet of length, or for every 1 centimeter of width, there's 4 centimeters of length. It doesn't matter. Whatever unit I put in there, the ratio is 1:4. So the next question is, well, what happens if units aren't the same and we can't change them like we did here? Let's say we go for a drive and we drive 365 miles, 7 hours. Here I cannot convert miles into hours, and I can't convert hours into miles. They are different units. They're going to be staying different units. This is what is referred to as a rate. And that is the first big difference between a ratio and a rate. A ratio compares 2 numbers with the same units or same labels. A rate compares 2 numbers with different units or different labels. Go back to the language we used last semester, different name. Second thing that's different is, well, a ratio is often just reduced and left wherever it comes. A rate is almost always reduced to something called a unit rate. Just like a unit ratio, the second number was a 1. In a unit rate, the second number is converted to a 1. So the way we convert it to a unit rate is we look at the bottom number here, which is a 7, and we're going to divide both the bottom and the top number by 7. On bottom, it's pretty simple. 7 hours divided by 7 is 1 hour. On top, 365 miles divided by 7, what is that? 52.14857 about miles. Now, 2 things here. First, probably wouldn't write it out in that many decimal places. We'd probably round it off after 1 or 2 decimal places. Second is, once we've converted it into a unit rate like this, we often don't write it as that fraction like that. We would often, let's round it to 2 decimal places, so 52.14. And rather than writing it in a fraction form like this, we'd probably abbreviate it like this as miles per hour. The fraction is hidden in the units. It's still there, but we don't write it out in the full form like this anymore. In fact, often we'll get rid of that appearance completely. And we might write it as 52.14 mph instead of miles/hours. The key is when we see something like that, we have to understand what it really means. Let's say that on that trip, we averaged 24 mpg. What does mpg stand for? Miles per gallon. So whenever we see this, we have to be thinking this is 24 miles for every 1 gallon. Because this is the form we need it in to calculate with. If we want to know how many gallons it's going to take to go a certain distance, we have to set it up like that. If we need to know how many miles we can go on a certain number of gallons, we have to have it set up like that. That's the form that we need it in order to work with it for any of the applications we're going to use it for. Well, let's look at some examples of rates and ratios. Let's keep going with rates for now since we're working. One example of rates that's important in mechanics, let's say you have a pulley that turns 3,420 times. (3,420 revolutions), 3 minutes. Well, if we write that as a rate, 3,420 revolutions out of 3 minutes. We need to convert that into a unit rate. Divide by the number, not the unit, but just the number on bottom, the 3. 3 minutes divided by 3 is just 1 minute. 3,420 divided by 3 is 1,140 revolutions. So it's 1,140 revolutions in 1 minute, or 1,140 revolutions per minute, like that, or 1,140 RPM, revolutions per minute. Again, if we see either of these two, we need to be thinking this, because this is the form needed in to do calculations. You might work. Let's say you earn gross pay. It's way easier. Of $680 for 40 hours of work. Rate here, $680 for 40 hours. Again, we want to convert that into that unit rate, so we're going to divide by 40. 40 hours divided by 40, of course, is just 1 hour. 680 is, divided by 40 is 17. $17 per hour. So that is $17 per hour. That one doesn't have a fancy abbreviation like RPM or MPG. What examples of rates? You know, we see rates all around us. Use them all the time. Let's go back to some ratios. Now, some of these ratios may be applicable for construction, some not. Some are mechanical, but we're going to do a different combination. One ratio that's pretty common. I'm going to warn you, you're going to have to use your imagination here because I'm going to draw pictures. And my artwork sucks. I'm not going to lie to you. So anytime I draw pictures, it requires you guys to be creative and use your. So if you look really, squint a little bit, those look kind of like gears. You have gear ratios. Well, gear ratios really are just comparing the size of one gear to the size of the other gear. But for two gears to mesh, the distance between teeth from one tooth to the other has to be exactly the same on both gears. Otherwise, they won't mesh together at high speeds. So we can find the size of each gear simply by counting the teeth. So a gear ratio is defined to be the number of teeth on the driven gear compared to the number of teeth on the driving gear. How do I know which is which? Well, the driven gear is the one that's connected to power. If I separate the two gears, the driving gear is the one that's connected to power. If I separate the two gears, the driving gear will keep turning because it's connected to power. The driven gear will stop because it's only turning because the first gear was driving it, was forcing it to. So that means I need more information over here to create a gear ratio. This might require a little bit more stretch of the imagination. And that looks like a shaft with a small electric motor on it. That large gear now, if we were to separate the two gears, that large gear would keep turning. It is the driving gear. If I count the number of teeth, it has 15 teeth. The small gear has 9 teeth. So the 9 teeth is the driven gear. If I separate them, it stops. 9-tooth gear stops. The 15 tooth is the driving gear because it is hooked to the motor or to the power. So it's a 9 to 15 gear ratio, which of course we can reduce. Both of those numbers divide by 3. 9 divided by 3 is 3. 15 divided by 3 is 5. 3 to 5. Now, a gear ratio is very important. It describes a lot of things. Not only does it describe the size of the gears compared to each other, it describes the RPMs of the gears. The smaller gear is going to turn at higher RPMs. So that gear ratio describes the ratio of the RPMs between the two. It describes the ratio of torques between the two gears. The torque on the shaft, I should say, between the two gears. Transfer from one to the other. So there's a lot of important mechanical calculations that are based off of that gear ratio. Another mechanical example. Actually, I didn't do too bad of a job on that one, did I? Yes, those are pistons, those are cylinders. Really good compression ratio. Kind of proud of that sketch. Oh, I shouldn't be so shocked when something I draw actually looks like what it's supposed to be. A compression ratio compares the expanded volume this is the volume of air above the head of the piston, above in the top of the cylinder, the compressed volume. So the compressed volume is top dead center. The piston is at the top of its stroke, the smallest possible volume of air above the piston. Let's say that this is 60 cubic centimeters. Expanded volume is when the piston's at bottom dead center. The most volume, most air possible above the top of the piston within the cylinder. Let's say that is 480 cubic centimeters. By the way, the difference between those numbers is called the displacement of the cylinder. There, the expanded volume is 480 cubic centimeters. Compressed volume of 60 cubic centimeters. Now the cubic centimeters cancels out. Units go away. Both 480 and 60 can actually be divided by 60. 480 divided by 60 is 8. 60 divided by 60 is 1. Now, once again, we leave that as 8 to 1 rather than just saying an 8 ratio. It's 8 to 1 compression ratio. Grade is an important ratio in construction. Grade is dealing with how steep the incline of land is, the flow of the land is. Grade compares the rise of the land to the run. So if I have land that rises 30 feet in a run of 240 feet, my grade is rise to run. 30 feet, 240 feet. Now, once again, the feet cancel out, and those numbers can be reduced. Actually, in this case, both of them can be divided by 30. 30 divided by 30 is 1. 240 divided by 30 is 8. That's a 1/8 grade, or a 1 in 8 grade. Now, standard practice, grades are typically expressed as a percent. And we'll look at how we can convert those into a percent later on. We might get to it today, otherwise it might not be till Thursday. Grades are very deceiving, by the way. 6% grade is saying there's 6 feet of rise, 100 feet of run. Now you look at that and say, well, that's not very steep. That's pretty close to flat. But how many of you are familiar with Highway 8 over by St. Croix Falls? Seems pretty steep, right? That is actually, I believe, an 8% grade. That's only 8 feet of drop and 100 feet of run. Seems a lot steeper than that. That's what it is. Actually, for a state or federal highway, that is the limit that is allowed, is 8%. Actually, they're talking about changing it to 7% a few years ago. County roads, you'll find those that are way steeper than that, but you won't find state or federal roads that are steeper. Let's talk about specific gravity. Specific gravity is actually important if you get into structural engineering side of construction, because it talks about the strength of materials. It really talks more about the density of materials. But it's really a matter of the density of the material compared to the density of water. And what it is it's really the mass of the material compared to mass of an equal volume of water. What really describes, like I said, is the density of the material. If the ratio of the specific gravity is 1, that's telling us that the density of our material is the same density of water. If it's higher than 1, well, also, by the way, if the specific gravity is less than 1, it's got lower density than water. That means it's going to float. Some construction applications, as you can imagine, there's some could be beneficial to have material that floats. If the specific gravity is greater than 1, it's not going to float. It's going to sink. Kind of like steel. Steel is way, way denser than water. You throw a steel beam in the water, it sinks rather quickly. How do they get a steel ship to float? Well, gravity of air is way less than water. There's my usual artistic ability. Steel ship floats because it's not solid steel, it's hollow. Air inside here. So when the level of the water gets up high enough so that the low density of the air cancels out the high density of the steel, it actually will balance out and it'll float. You can actually calculate, this is actually a very important engineering calculation. They can tell before they put a boat in the water exactly where the water line will be by calculating the density of the steel, the amount of air in it, the density of all the materials and equipment in that boat. They can tell you exactly where the water line will be on the outside of that boat, which is important for military applications because you have certain things, certain ports that have to come out below water and other things that have to come out above water. Well, let's talk about the big set of rates that comes out in construction for you guys. That's dealing with a roof. When you deal with a roof, there are actually 2 descriptions of how steep that roof is. There's roof slope, and there is a roof I don't know if Scott or Chris has addressed this with you all yet. They are not the same. Many people use them as though they are the same, but they are very, very different. Slope is rise over run. Just like it is mathematically in our algebra that we did last semester. So what that means, if I come over here to this truss, this roof line here, this is the rise. And let's say that that is 8 feet. The span of this truss is 24 feet. The run is the horizontal distance of the slope, just like it was with the grade, is the horizontal distance of the slope. Here, the run would go from here to here. In a typical standard truss, it's half the span, 12 feet. So the slope for this would be 8 feet of rise, 12 feet of run. Feet cancel out. Now we could reduce that, but we're just going to leave it. Slope is typically given out of 12. It's called a unit slope. It's inches of rise for every 1 foot of run, or for every 12 inches of run. So an 8-12 slope, it does mean that there's 8 feet of rise for every 12 feet of run, but it also means there's 8 inches of rise for every 12 inches of run. Comes back to that idea of a ratio being unitless again. It doesn't matter what units we put on there, it'll hold. Technically, the slope comes from 8 inches of rise for every 12 inches of run, but it can be applied as feet or whatever units we want to. That's what we're typically seeing, an 8-12 slope, a 6-12 slope, a 4-12 slope, 10-12 slope, whatever. Pitch is slightly different, although we use the term pitch many times when what we're actually describing is the slope. Pitch is height for span. So over here, the height is still the 8 feet that we had for the rise. The span is the 24 feet. 8 feet of height, 24 feet of span. Feet cancel out. We will reduce a pitch. Both of those numbers divide by 8. 8 divided by 8 is 1, and 24 divided by 8 is 3. That is called a 1/3 pitch. So the question is, why is there a difference, and what does it matter? The difference really comes from what type of framing you're using on the roof. Slope, typically used to describe trusses. A truss, of course, shows the pre-built, built in a factory. Slap it up, it's going to hold, whatever. The reason we use slope to describe trusses is this 8-12 ratio here. If we use our trig functions, it gives us all the different angles that we need to cut for like cutting the top chords to the right angles and cutting the butt cut on our bottom chord and stuff like that. It helps, trig allows us to use that slope to find all those angles on that truss. Pitch is more commonly used when you have a conventional frame. Of course, by conventional frame, I mean a ridge beam and rafter system. I kind of hesitate to use that term conventional framing anymore because it is not any longer the conventional way of framing it. Trusses are kind of the standard or common way of framing now. I'm using a beam and rafters. The heavy timber framing is really only for specialty things now, very, very expensive structures. In fact, even many of those are going to some form of a truss anyway. But what pitch describes is if you have top of your wall here, you're going to set your ridge beam up above it. Obviously, you have to have a post sitting on your wall to support your ridge beam. How high do you put your ridge beam, the top of your ridge beam, above the top of the wall? Well, a pitch of 1/3 is telling us that you take the span here, let's say that's 30 feet. Well, what's 1/3 of 30 feet? 10 feet. So the top of the ridge beam would be 10 feet above the top of the wall. So that's what the pitch describes, is how high, how far above the top of the wall do we set the top of the ridge beam to get the desired slope on that roof.
What's called the attic?
That'll form the attic, yes. The interesting thing about pitch is the ridge beam doesn't necessarily have to be in the center. If I put the ridge beam over here, as long as it's still 10 feet above the wall, that's still a 1/3 pitch. That's why a lot of older houses you might see that they are set up like that, a little bit off, different slope on one side or the other. So the pitch doesn't care; it doesn't have to be a common roof or same slope on both sides. Okay, so we are at a time where I would normally take a break. What I'm going to do, since I realize that most of you are, pretty much all of you are at home and are going to have to be coming in, you have a 12:30 class with Scott. What I'm going to do is I'm just going to keep going rather than taking a 10-minute break, and I will end class 10 minutes early. So rather than getting done at 11:20, we'll get done at 11:10. Now that includes work time, so we'll get done a little bit sooner than that because they give you a little bit of time to get started on your homework. But that'll give you, since I realize this, not only is your travel time to get from home to get here to school for Scott's class at 12:30, that's also your lunch break for all of you. Give you a few extra minutes to grab lunch and get here for Scott's class this afternoon. If you need to get up, get something to drink or go use the restroom or stretch your legs or whatever, if you're at home, I can't stop you. But even if you were in the room here, feel free to do it at any time, whatever you need to. So, homework related to ratios and rates. The big book. Hang on to that packet from yesterday because we're going to be using that packet off and on for the next few weeks. And we got a few other packets that we're going to put into the mix here in the next week or two. And then we'll come back to that other one, the trusses. But for now, in the big book, on page 133 to 134, exercise 4-2, odd number problems. So 1 through 31, the odds. So that'll be your homework dealing with ratios and rates. Like I said, we're just going to push right on into the next piece, the next topic. So we can get you guys out a few minutes early. And that is proportion. What is a proportion? A proportion, there's actually several applications of proportion. A proportion, in the simplest aspect, is either two ratios or rates, two rates, that must be equal. Something called proportional if something is described as being proportional, that means it has two values always have the same ratio. Or again, or rate. More specifically, directly proportional or direct proportion relationship, direct relationship. Let's talk about proportions here. We said a proportion is two rates or ratios that must be equal. Let's look at a gear ratio. We had that example up above where we had a 3-to-5 gear ratio. And let's say we have a machine that requires a 3-to-5 gear ratio between the motor and the interface with the rest of the machine. Well, let's say that we are installing a new motor on there, and the new motor comes with a gear on it that has 35 teeth. We need to install a gear on the machine to mesh with the motor that has the correct number of teeth. How many teeth does it need? Well, we require a 3-to-5 gear ratio. 35 teeth goes with the motor. That is the driving gear. Remember, the bottom number is the driving gear. 35 goes on bottom. Careful. To find that number on top, we have two different ways we can go about it. The basic way is we could look at the 5 and say, what do we multiply 5 by to turn it into a 35? That'd be 7, right? 5 times 7 is 35. So 3 times 7 is 21. So we would need a gear with 21 teeth to go on the machine so it would mesh with that motor to give us the proper ratios, the proper distribution of speed and power and everything else throughout that machine. Well, here this one was pretty simple because it was just 5 times 7 to give us 35. What if it's not that simple? How would we find that number? What if we had a gear ratio of, well, let's say 2 to, I end up with fractions here. Let's say we need to maintain a 2 to 7 ratio, and we have a bottom number here that is 40. I'm not talking about gear ratios here because we can't have a decimal number of teeth, but we need to maintain this ratio. Find out what would we multiply 7 by to turn it into 40. Well, that's going to be kind of tricky to do. What we can do to find that is we can work backwards. We can do 40 divided by 7. Well, 40 divided by 7 is 5.7142. What we're going to do then is we're going to have to, that was what we would multiply the 7 by to turn it into a 40. That number, 5.714, whatever. That's what we're going to multiply the top by. Well, rather than do the division first and typing it back in, we can just do this. It's 2 times 40 divided by 7. We can fudge our order of operations a little bit here and just multiply 2 times 40, then divided by 7, giving us 11.42857.143 approximately. Where did all that come from? Well, there's 2 ways we can get there. We can look at what we just did and realize that what we are multiplying is always going to be the 2 numbers that are diagonal with each other. It was 2 times 40. The 2 and the 40 are diagonal with each other. What we divided by was the number that's diagonal to our missing number. The 7 is diagonal to our missing number there. That's what we divided by. So my ratio over here, 3 to 5 is how much out of 35? Could have done 3 times 35. Those 2 numbers are diagonal to each other. 105. Then divided by the 5 because it's diagonal to our missing number. Divided by 5 is 21. That would have given us the 21 up there. Exactly what we had here. This shortcut is called cross multiply. Divide. It actually comes from a little bit more general process. You know, it works out, we could justify it by what I did over here with the fractions. But there's a more general process. I'm going to put some variables in here for a second just to illustrate it, but I'll come back to numbers in just a second. A over B has to be equivalent to C over D. Keyword there is they have to be equivalent, which means that symbol there is an equal sign. They are equal, so this is an equation. When dealing with an equation, if you remember from last semester, we can add, subtract, multiply, or divide from either side as long as we do the same to both sides, and it'll still be equal. It won't change the balance of that equation. Here's what I'm going to do. I'm going to multiply both sides of this by B. Get rid of the B over here. So I have A equals times b over d. Then I'm going to multiply both sides by d to get rid of the d over here. So I have a times d times b. Well, if I look up at what I started off with, a over b, you see that these products here are the diagonals, called cross products. A times d is just a times d. C times b is just c times b, or b times c, however you want to look at it. Those diagonal products, or cross products as they're called, have to be equal. So if I have portion, like 4 over 9, has to equal 12 over x. Notice the missing number doesn't always have to be on top. I can cross multiply. The cross products have to be equal. 4 times x, 4x. Going on this diagonal, 9 times 12 is 108. Those cross products have to be equal. 4x has to be equal to 108. I can solve that equation by dividing by 4. So, now, solving that equation by dividing by 4 kind of puts us back in that shortcut we were learning before, the cross multiply and divide. We cross multiply to get the cross products, and then we just divided by the 4 to get the result. The reason I show you both processes is if we have something like this, x over 9 equals 8 over 36, where the missing number is all by itself in one section of the proportion. X is sitting up there all by itself, nothing else in the way. Somebody looking at the door? Nothing else with it up there. Then the easiest way to solve this is to just do that cross multiply and divide. The two numbers that are diagonal with each other here are the 9 and the 8. So we do 9 times 8, 72. The number that's diagonal with our missing number is the 36. So we divide by the 36. 72 divided by 36 is 2. X here equals 2. That's the simplest way to do that. We would have got the same answer had we did the full cross multiply and create the equation. We cross multiplied this way, 9 times 8 is 72. We're going to multiply this diagonal, x times 36, 6x. And of course, 36x equals 72. Dividing by 36, 2. We get the same result, it's just way quicker here. So why would we ever want to do this longer process? Well, because not all of our proportions are going to be that simple. We might have 5 over x plus 2 equals 35 over 84. In this case, x is not by itself in that little spot on the proportion. It's x plus 2 rather than just x. And in this case, it's going to be easier. It's going to give us less mistakes if we do that full cross multiplication. 5 times 84 is on this diagonal. 5 times 84 is 420. On this diagonal, we have x plus 2 times 35. Well, it's a little bit different than what we're used to seeing, but this is just distributing. I can do 35 times x is 35x. 35 times positive 2 is a positive 7. So these two cross products have to be equal. 35x plus 70 has to be equal to 420. Now we can solve that equation. Subtract 70 from both sides. 5x equals 420 minus 70 is 350. And then to get x by itself, we divide by 35. Just like with any of the equations we solved last semester, we said we could always take that result, plug it back in for the variable, and verify that it's true. We can do the same thing here. If I put 10 in here for x, that's 10 plus 2. 10 plus 2 is 12. Is 5 over 12 equal to 35 over 84? Yeah, it sure is. 35 is 5 times 7. 84 is 12 times 7. Those are equivalent fractions. Well, there are two types of proportionality that we have to deal with. Well, first of all, let's look at 3/4 compared to 9/12. We know those are equivalent because 9/12 reduces to 3/4. I can divide both numbers by 3 to get 3/4. When I set up a proportion, there are often different ways I can set it up that will give me the same result. It will be an equivalent proportion. For example, I might have similar figures. We'll look at similar figures way more as we go on with them. But similar figures are two figures where one is just an enlargement or a reduction of the other. Let's have that triangle and this triangle. So let's say that triangle there, the big triangle, has sides of 6 inches, 15 inches, and 8. This one has sides of 4 inches, 10 inches, and 12 inches. They are a reduction of each other. But let's say that I'm going to swipe off this 12 inches here for a second. I'm going to say I don't know the size of that side. But we do know that it is this related to this bottom side of the other figure. If I want to find that dimension of x, I look at corresponding sides. X, of course, corresponds with the 18 inches. My other sides also have corresponding sides, though. 4 inches corresponds with the 6, and 10 inches corresponds with the 15. To find x, I'm going to have to use its corresponding side. I'm going to have to use the 18. For what else I use with it, I can choose a little bit. Let's say I want to use the 6. 6 corresponds with the 4. I'm going to have to use the 6 and the 4. Well, I could write this as 6 compares to 4 in the same way as 18x. Why does that work? Well, 6 and 4 are a pair of corresponding sides. 18 and x are a pair of corresponding sides. But also, 6 and 18 are from the same figure, and 4 and x are from the same figure. In each of these proportions, there's a relationship in both directions, both vertically and horizontally. I cross multiply and divide here. I go the other way. 4 times 8 is 72. 6 is diagonal with the missing number, so I divide by 6, I get 12. X equals 12. But I could have set this proportion up slightly different. I could have said 6 and 18 are in the same figure, so I'm going to have 6 compared to 18. 6 corresponds with the 4, so 4 goes over here. X corresponds to the 18, so X goes over there. Notice 6 and 4, once again, a pair of corresponding sides. 18 and X, a pair of corresponding sides. Rather than being one above the other, they're side by side now. 6 and 18 are from the same figure, go together. 4 and X are from the same figure, they go together. It doesn't matter what direction the relationships go in, the same relationships exist. They just went vertically for the same figure instead of horizontally here. But notice when we cross multiply, it's going to be the exact same numbers. 18 times 4 is still 72, and we're still dividing by the 6. Get 12. You'll notice even though the proportion was rearranged, we get the same result. Because these are really the same proportion. I exchanged these two numbers, the 10 and the 18 and the 4, but I get the same cross product, same results. So there are a lot of ways to, in many of these problems, just because you don't set up the exact same proportion doesn't mean you did anything wrong. There's several different proportions you can set up. They'll give you the same answer. You could have done the 4 over 6 equals x over 18 if you wanted to. Notice that's just this proportion. I flipped it upside down. When I cross multiply, it's still 4 times 18 is 72, and divided by 6 gives me 12. X is still 12. Still multiplying the same two numbers even though they're in different locations. Still dividing by the same number even though it's in a different. I put the term direct up there. Direct relationships or direct proportion is a true proportion. A direct proportional relationship is a constant ratio or rate. That's basically what we've been looking at so far. I have a roof. It has a rise of 9 feet and a 36 feet. My slope, looking at my rise, 9 feet. My run, however, is not the 36. My run would be half of that, 18 feet. Now, I don't want to reduce this to 1/2. 9 over 18 would reduce to 1/2 if I fully reduced it. I want slope to be expressed as something over 12. So I'm going to take my 9 over 18. I can cancel out the feet. I don't need to worry about the feet. And I want to know what would that be out of 12. So I can set up that proportion. Cross multiply. 9 times 12 is 108. Divided by 18. 108 divided by 18 is 6. That would be 6 out of 12. This is a 6/12 or 6 out of 12 slope. That is direct proportion. If I want to maintain a 6/12 slope, I'm sure you guys have seen this symbol before. This symbol here is the symbol for a roof slope. That is indicating a 6/12 slope. I realize I'm a little skinny on my truss there, but if I want to maintain a 6/12 slope, but increase my span here to 60 feet instead of 36 feet, and what my height is. I have a 6/12 slope. 60 is not my run. My run would be half of 60 or 30 feet. That goes on bottom because it's rise over run. I'm going to cross multiply and divide. 6 times 30, 180. Divided by the 12, 8. 15 feet. Because this is a direct proportion, whenever the run gets larger, rise has to get larger in a proportional amount. And that is a direct relationship. If one value gets larger, the other value gets larger. Likewise, if the first value, in this case the run by this example, got smaller, the second value would get smaller. Again, in a proportional amount. That is a direct relationship. It is this constant ratio. For example, we might have a direct relationship where we have let's say that in 80 hours, crew can sheetrock. That's just hanging the sheetrock for 4 houses. Ratio, 80 hours, 4 houses. I'd ask, how long would it take to do 11 houses? Well, we set up our proportion. Now, technically, this is not a ratio, is it? I am comparing hours to houses, not comparing 2 units that are the same. But it doesn't matter. We said it could be a rate or a ratio or a rate. Here it's a rate. We're going to put the 11 houses goes down here because, well, houses have to go with houses. Find the missing number, we'll cross multiply. 80 times 11, 880, divided by 4, 220 hours. So again, the number of houses got larger, the amount of time it takes to do those houses gets larger in a proportional manner. With any sort of direct proportionality, you can always find something called a constant of proportionality. And many of you in this case were probably thinking that, wouldn't it be easier just to do 80 hours divided by 4 houses, get that unit rate, 20 hours per house, and then go from there. 20 hours per house times 11 houses. Would have got the same answer. A little bit more work, but it gets you to the same result. So yes, when we're dealing with a direct relationship like this, you can divide out one of the rates or ratios and get that constant and use it. Next piece, I don't like the fact that they refer to this even as proportional. Call it inversely proportional. To me, it's not proportional. It's not constant rates. It's really what I refer to as inversely related. There is a slight difference between those two terms. Let me talk first about inversely proportional. Inversely proportional means one ratio or rate is equal to the inverse of another ratio or rate, of course. What is an inverse? Well, an inverse, when we're talking about a ratio or rate, if we were talking about a fraction, it would just be a reciprocal. So let's go back to our ratio, our gear ratios, our teeth. But look at speed. Ratio of RPM is inversely proportional to the number of teeth. In other words, inversely proportional to the gear ratio. So what does that mean? Well, let's say we have gear with 12 teeth. Meshing with a gear with 8 teeth. Not telling you which one is hooked to power, it doesn't matter in this application. But let's say that we know this gear with 8 teeth is turning at 400 RPM, 400 revolutions per minute. How fast is the gear with the 8 teeth turning? Well, my ratio of teeth is 12 to 8. 12 teeth to 8 teeth. I'll let this be X RPM for the speed of the second gear. A ratio of RPM, 400 to X, putting the bigger gear first again. Inversely proportional, though, means I compare one ratio to the inverse of the other. 12 over 8 does not get compared to 400 over X. It gets compared to its inverse. I'm going to show you an easy way to do this. So we cross multiply 12 times 400, 4,800. We divide by the 8. Gives us 600. X is 600. So this smaller gear is actually turning at 600 RPM. That's what inversely proportional means, is you make the two ratios or the two rates, you invert one of them, you flip it over, and then you set them equal. I hate that description. Inversely proportional is not proportional. It is, it's proportional to the inverse, still. Inversely related. Sometimes referred to as inverse variation. And we'll talk about direct variation and inverse variation sometime next week, I believe, at some point before we're done here. Next couple weeks. Inversely related means rather than being equal ratios, we have equal products. So if I look back at that gear ratio example, I had 12 teeth meshing with 8 teeth, and I had 400 RPM, X RPM. From one gear to another, the product of the teeth times the RPM has to be equal. So for the first gear, I have 12 teeth times 400 RPM. The second gear, I have 8 teeth times X RPM. And now I just solve that equation. 12 times 400 is 4,800. 8 times X is just 8X. I solve by dividing by 8. 4,800 divided by 8 is 600. X is 600 RPM. Just what we had up above, but it's just way less confusing to me. Rather than trying to remember, okay, we get the two ratios, then we got to flip one of them over. Way less confusing to me. Just it's a product. You have the two products, you set them equal to each other, and you solve. This can happen if you look at a pump. Let's say we have a 8 FM pump. And drain a basement. Get into construction, get into contracting. This is something, unfortunately, you're going to have to deal with more often than you'd like. You dig a foundation, might even have a basement poured, and you get a big storm, full of water, got to pump it out. 8 CFM pump can drain a basement. In 90 minutes. How long would 12 CFM pump? So again, CFM is cubic feet per minute. It makes sense that a larger pump is going to take less time. And that is the key to inverse relation. Whether you call it inverse proportion or inverse relation, if one number gets larger, the other number has to get smaller. We get a bigger pump that pumps the water faster, time it takes gets smaller, it takes less time. So this is a constant product. Our constant product here is the size of the pump times the time it takes to drain the basement. So we have 8 CFM times 90 minutes is the first pump. Well, the second pump is 12 CFM times X. We don't know the number of minutes. We're trying to find. 80 times 90 is 720. Or sorry, 8 times 90 is 720. 12 times X is 12X. So I solve by dividing by 12. 60. So that takes 60 minutes. Makes sense. 1.5 times larger pump. Divide by 1.5 to get the time it would take. So, homework for the second hour of class. Also in the big book, page 142 to 145. This is in the unit exercises. Problems 15 to 31, the odd. So normally this is about what time we'll be finishing every day, a little bit right around 11 or so. We're going to skip our 10-minute break, like I said, since you guys are working virtually. Get up and take your break whenever you want to if you need to. Usually about 10 minutes of work time. Sometimes we'll finish a little before 11 o'clock because they try to include about 10 minutes of work time with each hour of lecture. So that would actually put us closer to 10:50 some days. But it'll be about that 10:50 to 11 o'clock that we'll be getting done each day. Like I said, that skips your 10-minute break, and then that's that 10 minutes or so of work time with each hour of lecture. I will stay on the network if you guys want to work on homework and ask questions. I'll be here until everybody logs out. Otherwise, like I said, it gives you that extra time to grab lunch and get here to WITC for stats classes. Does anybody have any questions? Okay, well, with that, I'll end the recording, and I'll be hanging out here.